Isro-Vssc Technical Assistant, Electrical Engineering previous year question paper with a detailed solution, exam held in 2017. This is a part 3 video. Up to question number 40 we discussed in the last two videos. Question number 41. The current waveform in a pure resistor at 10 ohm is shown in given figure. Power dissipated in a resistor is. Answer is option D, 270 watt. Power dissipated in resistor P equal to I square RMS into R. Given waveform is a triangular waveform of amplitude 9 ampere. Therefore, Im equal to 9 ampere. Therefore, IRMS equal to Im by root 3, which is equal to 3 root 3 ampere. P equal to I square R. Substituting the value of IRMS square into R. Substituting the values of IRMS and R, we get power as 270 watt. Question number 42. Three coils are connected as in the following figure with self-inductances and mutual inductances as indicated. The effective inductance of the circuit across the terminal AB in the figure is. Answer is option C, 11 Henry. Coil 1, that is considered as 4 Henry coil, and coil 2 is considered as 5 Henry coil, and coil 3 is considered as 6 Henry coil. Here coil 1 4 Henry and coil 2 5 Henry are in series opposition. That is, dot present in coil 1 is at the starting end and dot present in the coil 2 5 Henry is at the ending position. That is series opposition. M12 equal to, therefore as it is series opposition, M12 is minus 1 Henry. Coil 2 5 Henry and coil 3 6 Henry are series addition as the dot present in both coils at the end positions. M23 is 2 Henry. Coil 1 and coil 3 are in series opposition. M31 equal to minus 3 Henry. Total inductance L equivalent equal to L1 plus L2 plus L3 plus 2M12 plus 2M23 plus 2M31. Substituting these values, we get total inductance L equivalent as 11 Henry. Note: equivalent inductance of two inductors in series connection. For mutual aiding, when polarity dots are present at the same end, L equivalent equal to L1 plus L2 plus 2M12. For mutual opposing, when polarity dots are present at the opposite ends, L equivalent equal to L1 plus L2 minus 2M12. Equivalent inductance of two inductors in parallel connection. For mutual aiding, L equivalent equal to L1 L2 minus M12 square divided by L1 plus L2 minus 2M12. For mutual opposing, L equivalent equal to L1 L2 minus M12 square divided by L1 plus L2 plus 2M12. Question number 43. The three-phase balanced source in the given figure delivers 1500 watt at a leading power factor of 0.844. Then the value of ZL in ohms is approximately. Answer is option D, 90 angle minus 32.44 degree. Given power P equal to 1500 watt. Line voltage VL equal to 400 volt. This we can get from the figure also. Power factor cos phi equal to 0.844. Therefore, phase angle phi equal to cos inverse of 0.844. We get it as minus 32.44. Negative due to leading power factor. We know total power in three phase P equal to root 3 VL IL cos phi. Therefore, after rearranging we get line current IL equal to P divided by root 3 VL cos phi. Substituting the values of P, VL and cos phi, we get IL as 2.656 ampere. Given three-phase balanced source is in star connection, we can this identify from the figure itself. Therefore, VP, phase voltage equal to VL by root 3. Substituting the values of VL, we get it as 2.656 divided by root 3 and IL equal to IP, which is equal to 2.656 ampere. Now the impedance ZL equal to VP divided by IP. Substituting the values, we get ZL as 90 ohm. 90. Question number 44. A single phase transformer when supplied with a 220 volt 50 Hz has eddy current loss of 50 watt. If the transformer is connected to a voltage of 330 volt 50 Hz, the eddy current loss will be, answer is option B, 112.5 watt. Given F equal to 50 Hz, eddy current loss P1 equal to 50 watt, V1 equal to 220 volt and V2 equal to 330 volt. Here V by F is not same in both cases. Hence flux density Bm is not constant. Pe1 by Pe2 directly proportional to V1 into F divided by F into V2 whole square. That is Bm directly proportional to V by F. Substituting the values of Pe1, V1 and V2, we get the values of Pe2 as 112.5 watt. Question number 45. In an AC series motor, the EMF is answer is option C, 0 at the brushes and also maximum in the coils undergoing commutation. In an AC series motor, the EMF is 0 at the brushes and maximum in the coils undergoing commutation. Because brushes are functionally present at a neutral or interpolar axis, so that 0 EMF is induced at brushes. AC series motor is a commutated series wound motor. The stator's field coils are connected in series with the rotor windings through a commutator. At the time of commutation, a huge voltage induces in the short circuiting coil because of transformer action. It causes sparking at brushes. To reduce the induced EMF due to transformer action in the armature coils while commutation period, to facilitate smooth commutation, the following measures are taken. By shunting the winding of each commutating pole with non-inductive resistance, the flux per pole is reduced and the number of poles are increased. The frequency of supply use is reduced. Preferably a single turn armature coil is used. What is the equivalent resistance between A and B in the following diagram? Answer is option A, R. Given circuit is a balanced Wheatstone bridge, that is R by R equal to R by R. Hence there is no current passing through that inner bridge network. So neglect that part. Therefore the modified circuit is like this. Here R and R is series connection. So the effective resistance is 2R parallel to R. The equivalent resistance between A and B is 2R parallel to R. We get RAB is R. What is the equivalent resistance between A and B in the following diagram? Answer is option D, 1 plus 2 root 3 ohm. As it is an infinite circuit and pattern of the network is repeating, we can think this logic that alpha minus 1 is also considered as alpha. Also alpha plus, not alpha, infinity. Infinity minus 1 is also considered as infinity. Similarly, infinity plus 1 is also considered as infinity. So just neglect the remaining portions. Consider those resistance, those equivalent resistance as R and connect across it parallel. That is when which resistor is going to repeat. From that resistance itself consider as R. So consider the modified circuit. 2 ohm and 1 ohm are considering. The remaining resistors equivalent resistance considered as R. Here 1 ohm is in parallel with the resistor R. Therefore 1 ohm parallel with R, which is equal to R into 1 divided by 1 plus R. We get R by 1 plus R. And here 2 ohm is in series with R by R plus 1. That is total resistance R equal to 2 plus R by R plus 1. That is R equal to cross multiplication. We have performing, that is 2R plus 2 plus R divided by R plus 1. Cross multiplying R plus 1 into R, we get R square plus R minus 3R minus 2 equal to 0. We get R square minus 2R minus 2 equal to 0. Solving by quadratic equation, we get R equal to 1 plus or minus 2 root 3. As 1 minus 2 root 3 is a negative value, hence equivalent resistance is 1 plus 2 root 3. 48. Let the resistance of a permanent magnet moving coil instrument be R ohm. What is the shunt resistor required to measure a maximum current which is 5 times the full scale deflection current of the instrument? Answer is option B, 0.25 R ohm. In a PMMC instrument, RSH equal to Rm by M minus 1, where Rm is Vm by Im and M is the multiplying factor. Present full scale division divided by previous full scale division, where RSH is the shunt resistance, Rm is the meter resistance, Vm is the potential difference across meter, Im is the meter current. Given Rm equal to R ohm, let the previous FSD current of PMMC is I, then present FSD current of PMMC is 5I. Therefore, M equal to 5I by I, we get M as 5. Substituting the value of M in the equation of R as such, we get R by 5 minus 1 equal to R by 4, which is equal to 0.25 R ohm. 49. If the current through a moving iron instrument is increased by 20%, what is the percentage increase in the deflecting torque? Answer is option D, 44. In moving iron instruments, the deflecting torque is unidirectional, acts in the same direction, whatever may be the polarity of the current. The deflecting torque TD equal to I square dl by d theta, where I is the operating current, L is the self-inductance, theta is the deflection. From this equation, we can also consider TD directly proportional to I square, so that the deflection torque of the moving iron instrument is proportional to the square of the RMS value of the operating current and change in self-inductance. Given when the current through a moving iron instrument is increased by 20%, then the deflection torque is D dash directly proportional to 100 plus 20, that is 120 by 100, that is 1.2 I whole square. That is TD dash equal to 1.44 TD. Hence the deflection torque is increased by 44%. Which of the following wave has a minimum form factor? Answer is square wave with a 0 DC value. Form factor is defined as the ratio of the RMS value to the average value of an alternating quantity. Form factor equal to RMS value divided by average value. Crest or peak factor is defined as the ratio of the maximum value to the RMS value of an alternating quantity. Crest factor equal to maximum value divided by RMS value. The form factor and crest factor for different waveform is, for sine wave RMS value equal to 0.707, crest factor it is root 2 or 1.414, and form factor it is 1.11. For triangular wave and sawtooth wave, RMS value is 0.577, crest factor is root 3, which is equal to 1.732, form factor equal to 1.154. For square wave, RMS value, crest factor and form factor all are 1. There are three voltage sources. Voltage source 1 gives 200 volt peak voltage. Voltage source 2 gives 100 volt peak, which lags behind voltage source 1 by 120 degree. And voltage source 3 gives 100 volt peak, which leads voltage source 1 by 120 degree. If these voltage sources and a 1 ohm resistor are connected in series, what is the power dissipation in the resistor? Answer is option B, 5000 watt. Given R equal to 1 ohm, V1 equal to 200 angle 0 degree, V2 equal to 100 angle 120 degree, V3 equal to 100 angle minus 120 degree. All three voltage sources are connected in series. Therefore, equivalent voltage is V equal to V1 plus V2 plus V3. Substituting the values of V1, V2 and V3. And the angle we can also write as cos theta plus j sin theta. So, 200 cos 0 degree plus j sin 0 degree plus 100 into cos 120 degree plus j sin 120 degree plus 100 into cos minus 120 degree plus j sin minus 120 degree. After solving, we get the total voltage V as 100 angle 0 degree volts. Therefore, Vrms equal to Vm by root 2, which is equal to 100 by root 2. Since R equal to 1 ohm, Vrms equal to Irms, that is Vrms equal to I into R. R is 1 ohm, so Vrms equal to Irms equal to 100 by root 2. Therefore, the power dissipation of the resistor P equal to I square Rms into R. Substituting the values of I, Rms and R, we get the total power dissipation in the resistor as 5000 watt. In the following circuit, the ratio of the heat produced in the resistor R1 to the heat produced in the resistor R3 is, answer is option B, 25:18. Applying current division rule across R3, we get I3 equal to R2 divided by R2 plus R3 into I1. Substituting the values of R2 and R3, we get I3 as 3 by 5 I1. The heat produced in the resistor R1 for time T will be H1 equal to I1 square R1 into T. that is I1 square R, value of R1 is R. Substituting that, we get H1 is equal to I1 square RT. The heat produced in the resistor R1 for the, it is not R1, it is R3. For the time T will be heat H3 equal to I3 square R3T, which is equal to 3, substituting the values of I3, 3 by 5 I1 whole square into 2 RT. That is, we get 18 by 25 into I1 square RT. The ratio of heat produced in R1 to the heat produced in R3 will be H1 by H3 equal to I1 square RT divided by 18 by 25 into I1 square RT. We get it as 25 by 18. Therefore, H1 is to H3 equal to 25 is to 18. When a DC motor generates maximum power, ratio of applied voltage to back EMF is, answer is option C, 2 is to 1. For a DC motor, from the power dissipation, PM equal to gross mechanical power developed, EBIA equal to VIA minus IA square RA, where V is the applied voltage, EB is the back EMF, IA is the armature current, RA is the armature resistance. For maximum PM, dPM divided by DIA equal to 0. So differentiating the equation of EBIA, we get V minus 2 IARA equal to 0. That is, IARA equal to V by 2. Substituting in voltage equation, V equal to EB plus IARA, we get V equal to EB plus IARA. We from the above equation, for maximum PM, we get IARA equal to V by 2. Substitute this value in this equation, we get V equal to EB plus V by 2. That is, V minus V by 2 equal to EB. Therefore, EB equal to V by 2. So that when DC motor generate maximum power, ratio of applied voltage to back EMF is 2 is to 1. 54. A shunt generator delivers a load current of 450 ampere at a 250 volt. Armature resistance is 0.01 ohm and shunt field resistance is 50 ohm. Calculate the EMF generated. Answer is option A, 254.55 volt. Shunt field current ISH equal to V divided by RSH. That is 250 by 50 equal to 5 ampere. For armature current IA, from the figure we can understand it is IL plus ISH. Substituting the values of IL and ISH, we get armature current IA as 455 ampere. Now generated EMF in DC shunt generated, E equal to V plus IARA. Substituting the values of V, IA and RA, we get generated EMF E equal to 254.55 volt. 55. In a DC generator, generated EMF is directly proportional to, answer is option B, pole flux. In DC generator, generated EMF E equal to ZP phi N by 60 ampere, and the other equation is E equal to V plus IARA, where Z is the conductor per pole, P is the number of poles, phi is the flux per pole, N is the speed in RPM, A is the number of parallel paths, IA is the armature current, and RA is the armature resistance, V is equal to terminal voltage. Thus, from the DC generated induced EMF equation, it is clear that induced EMF is directly proportional to conductor per pole. It is not speed, it is speeds, number of poles and flux per pole. In an induction motor, if the supply voltage is halved, the starting torque becomes, answer is option B, 1/4. The torque equation of a three-phase induction motor T equal to 180 divided by 2 pi ns into S E2 square R2 divided by R2 square plus S square X2 square. At the starting slip is equal to 1, TST equal to 180 divided by 2 pi ns into E2 square R2 divided by R2 square plus X2 square. From the above equation, we can say that starting torque of an induction motor is directly proportional to square of applied voltage when all other factors are constant. That is, TST directly proportional to E square, where E2 is the rotor side resistance and R2 is the rotor side resistance and E2 is the reactance, Ns is the synchronous speed. If the supply voltage is halved, then the starting torque becomes 1/4 of its previous value. 57. Moving an ammeter is used for the measurement of, answer is option C, both A and B, that is DC current and DC AC current. Note, Moving ion type ammeter can be used for measurement of AC and DC. PMMC ammeter is used for DC measurement. Galvanometer is used for detection of current. Hot wire type ammeter is used for AC measurement. Question number 58. In an LC circuit at resonant frequency, the magnitude of capacitive reactance is equal to inductive reactance. At a resonance, an RLC circuit behaves as purely resistive circuit. The inductive reactance and capacitive reactance are equal and equating the two gives the resonant frequency of the circuit. XL equal to 2 pi FL, XC equal to 1 by 2 pi FC. At a resonance, XL equal to XC. After substituting the value of XL and XC, we get F equal to 1 by 2 pi root LC. From this plot, at a resonant frequency, omega R, the current is maximum, that is Im. Impedance Z equal to R. At a half power frequencies, omega 1 and omega 2, the current is not maximum, it is Im by root 2. Impedance Z equal to root 2 R. Consider the following statements P1 and P2. P1. Beta of bipolar transistor reduces if base width is increased. Beta of bipolar transistor increases if doping concentration in the base is increased. Answer is option B. P1 and P2 are true. The common emitter current gain beta is the ratio of the transistor's collector current to the value of transistor's base current. Beta equal to IC by IB. A bipolar transistor consists of three differently doped regions. The emitter, base and collector regions as N-type, P-type and N-type respectively in an NPN transistor. The base region is physically located between the emitter and the collector and is highly doped. Tightly doped. Lightly doped. The collector surrounds the emitter region, making it almost impossible for the electrons injected into the base to escape without being collected, that is base width is kept small. This results in the value of alpha, base transport factor being close to unity and thus giving the transistor a large value of beta. So that when base width is increased, the common emitter current gain beta is decreases. When doping concentration in the base is increased, then depletion layer width decreases, due to which resistance across the base region decreases. So that collector current increases. Hence, common emitter current gain beta increases. The relation between alpha and beta. Alpha equal to beta divided by 1 plus beta and beta equal to alpha divided by 1 minus alpha. The last question of this video is 60th one. For a binary half subtractor, the correct set of logical expressions of output D, A minus B and X borrow are. Answer is option C, D equal to A bar B plus A B bar and X equal to A bar B. This is a truth table of half subtractor. For input 0, 0, difference is 0 and borrow is 0. For input 0, 1, difference is 1 and borrow is also 1. For input 1, 0, difference is 1 and borrow is 0. For input 1, 1, difference is 0 and borrow is 0. We can make the equation according to for which input the difference is 1. That is for A bar B plus A B bar. For borrow, output is 1 when A bar B equal to A bar B. Therefore, the equation of borrow is A bar B. Thank you.